So before we get into the question where are all these chemical elements come from, maybe we should ask one more basic question. So we learn in school that everything is made of atoms. But how do we know that? For example, think about a star, even our sun. Nobody has gone to the sun, took the sample, and come back, right? How do we know that the sun is made of atoms? In some sense, that's actually one of the major discoveries of our scientific progress, that we have good evidence that all the stars in the entire universe are made of atoms. And one very important tool for this is something called spectroscopy. You might have done this little experiment in your school that if you take a piece of a glass called prism, it's kind of triangular shaped glass, and if you let the light go through it, it would separate different colors in sort of rainbow-like stripe. And if you use a more advanced devices, then you can do this with much more greater precision, and you can take the light coming from the sun, let it go through this device, for example, called grating, and then you can separate light all the way from red to violet. And this picture here is actually supposed to be a single strip, but it wouldn't fit on this slide, so I chopped it up in many pieces and lined them up like that. So this is meant to be actually a single continuous spectrum of colors coming out from the sun. And if you look at this picture, I hope you will notice one thing which is strange. That some colors are missing, right? You see these black lines, which means that those colors are somehow missing in the sunlight. So what's going on there? And if you look closely at these missing colors, you actually can identify them as something you study in your laboratory. For example, if you go into a tunnel, you might have experienced the fact that your body all of a sudden looks like a dead corpse. And that's because the light used in a tunnel, in many of them, are based on sodium. They're called sodium lamps. And what's going on there, that inside the glass of that lamp or light, you have the gas of sodium in it, and the sodium emits light of very particular colors. They're always yellow. For a given chemical element, you know exactly what color would come out from the chemical element. At the same time, that is the only colors that particular chemical element can also absorb. So one element, specific colors, either absorption or emission. One chemical element implies very specific set of colors. So once you see these missing black lines in the sunlight, you can look at the particular color of these missing lines and say, aha, this is actually iron, this is actually chromium, and so on. So in some sense, these missing lines here are like fingerprints of chemical elements that exist inside the sun. So by studying these missing lines, you can tell what the sun is made of. So if you blow it up, you see many of these lines, and you can identify each one of them to a particular chemical element, which you can study in the laboratory. For example, this is magnesium, this is sodium, hydrogen, and iron. And you can see all of them have lines in different colors in different locations. So knowing these black lines, the absorption lines in the sun, you can tell exactly which line corresponds to which chemical element. But it's not the whole complete story. So when you think about, for example, our sun, the only thing you can see is the surface of the sun. You can't see straight into the interior or center of the sun because light doesn't penetrate through it. Sun is so hot and dense, light does not penetrate into it. It's sort of foggy, and you cannot see the center of the sun directly. And that was actually one of the problems when people ask the question, why does the sun shine? Do you know the answer to this question? Why does the sun shine? Well, we are getting all this heat and warmth from the sun. Without it, we cannot live. No biological system probably can exist on the earth. So that's very important for our existence. And of course, people debate a lot about this question, why does the sun shine, also from early days of science. And towards the end of 19th century, there was a famous physicist called Lord Kelvin, and who was known to be so famous and smart that pretty much every physicist had a great admiration to him. And he, of course, addressed this question, why does the sun shine? And of course, people also wanted to know how long the sun is going to last. that once people learned about the conservation of energy, it's clear the sun would not go on forever. Even the sun would have some limit when it exhausts all the energy it got. And Lord Kelvin said, well, the sun can't possibly last more than 20,000 years. And that's a kind of shocking statement. Human beings have been around more than 1 million years. So it sounds almost like tomorrow. But there was also counter-argument, for example, like Darwin, in considering evolution of the biological systems, and some record geological data coming from the sampling rocks from around the world. They believed Earth must be at least 300 million years old. Now here's a big difference in numbers. If the sun can't possibly last more than, say, hundreds of thousands of years, but Earth is much older than that, does it mean that sun was born much later, more recently, after a long history of the Earth? That doesn't quite sound right, right? So what Lord Kelvin was missing here, and so Lord Kelvin was actually wrong, was that he estimated the life of the sun based on the assumption that the sun shines basically out of the chemical reaction. So if you imagine that sun shining, it's like an explosion of dynamite or some kind of burning fuels and stuff like this, then certainly you can compute how long it can possibly last, because we know how much energy you can produce for a given amount of mass of some fuel. So that's what we did. But the biggest mistake he did was to assume that the chemical reaction was the only source of energy. And indeed, that was the most powerful source of energy back in those days, so it was a natural assumption for him. But he was not aware of this famous equation, E equals mc squared. So as you know, E equals mc squared had been proposed by Albert Einstein, and he proposed this equation, which was quite controversial at that point. But only thanks to this equation, we now understand why the sun shines. So it turns out that the sun is converting mass to energy. So what it's actually doing is this. The sun brings in two hydrogen nuclei, namely protons, together. It fuses 4 protons into a single piece of helium nucleus. But helium nucleus has only 2 protons, while you brought in 4 protons. So you need to convert 2 of the protons into neutrons. It turns out that's possible. There's such a reaction, and we'll come back to that later. It's called the weak force. And if you do so, you spit out 2 units of positive electric charge in a form of, it turns out, antimatter. They're called positron. And 2 unfamiliar particles called neutrinos, which are kind of ghosts. It sort of penetrates everything as far as we can see. And from this reaction, it releases a certain amount of energy, and in a unit we use in physics is 25 billion electron volts. So that's how the sun is producing energy. And the key to this is this, to pretend that you put all this stuff on a scale, and what you got initially are 4 protons. What you got after the reaction is a helium plus a little things like positron and neutrino. If you weigh them together, all the mass you got at the beginning is more than all the mass you ended up with. And that's kind of surprising, right? So if you imagine, for example, collision of 2 cars, it produces a lot of debris. But if you manage to scoop up every single piece of debris of these 2 cars and sum them up, that must be exactly the same as the sum of masses of 2 cars at the very beginning. We call that the conservation of mass. That's something we take for granted in our daily life. And if 2 of you got on the same scale, what you measure is the sum of the masses of you and your friend. Again, the mass can be just added together. It's not going to change. But what we see here is that's different. The sun, before the reaction, was a little heavier than after the reaction. So by releasing energy, what the sun is doing is actually keep getting lighter. As a matter of fact, the sun is getting lighter by 4 million tons every second. And the reason why that is important is because of this E equals mc squared. E is energy, m is mass. c is the speed of light. It's just a big number for the purpose of this discussion here. So what it's basically saying is that mass and energy are the same thing. So by getting lighter, the sun can release the mass as energy, and that's how the sun is shining. And at the same time, it releases this byproduct called neutrinos. So if you would like to answer the question, how do we know that this reaction is indeed happening inside the sun? There's an answer to this question. Namely, you can detect these neutrinos. And these neutrinos, such ghost-like objects, they can just penetrate the entire sun with great ease. It can penetrate the entire Earth with no problems at all. And as a result, there must be 100 trillion neutrinos going through your body every second. So the sun is converting mass to energy. That's what it's doing. That's how the sun shines. And this is far more powerful source of energy than any chemical reactions. So the Lord Kelvin was wrong. The sun is going to last a lot longer. But then the question is, can we really test this by detecting these weird particles called neutrinos? So that's the question next. How do we ever detect these neutrinos to find the proof that this is indeed happening at the center of the sun?